Hi, and welcome to my talk on the living roly-poly model. The purpose of this talk is twofold. One, to introduce the new constitutive model for nonlinear rheology of living polymer systems that are well entangled, and two, to test a particular hypothesis for shear banding, namely that of flow-induced scission in worm-like micelles. Okay, to begin with, what are living polymers? In what sense are they living? Well, living polymers are living in the sense that their polymerization reaction, these processes by which they're breaking apart and combining together, reach a dynamical as opposed to a stationary equilibrium. Polymerization never terminates in these systems. So this happens for worm-like micelles, that's the most common experimental system, but it also can happen in liquid sulfur and polymers with sticky end groups. We will at times assume a micellar chemistry in this talk, but the equations themselves should apply to all kinds of living polymer chemistries. Okay, and we're going to focus on two peculiar features of the rheology of worm-like micelles, one in the linear regime, one in the nonlinear regime. In the linear regime, if one subjects a worm-like micelle system to small amplitude oscillatory shear and then measures the loss modulus and the storage modulus over a range of frequencies and plots those parametrically, one recovers this semicircular shape, indicative of a material with a single relaxation time. It's very unusual. Then in the nonlinear rheology regime, as one increases the shear rate to which the material has been subjected, one finds this anomalous plateau in the stress, which indicates shear banding, that the system has split. In this intermediate shear rate regime, it splits into a low shear rate region and a high shear rate region. And the mechanism behind that is thought that somehow this underlying constitutive behavior is non-monotonic, that there's a range of shear rates for which, were the system to remain homogeneous, the shear stress would be decreasing with increasing shear rate. That's weird intuitively, but mechanically it's unstable. Such a system would have to break apart into a shear banded flow. Now, how does one get a non-monotonic constitutive curve? Well, one popular hypothesis for that comes from the VCM model, Vasquez, McKinley, and Cook. What the VCM model says is that, okay, the important thing about living polymers is that they do these reaction processes. They break apart, they come back together. So let's model that by a reactive dumbbell system, which is two species. You have short dumbbells that attach together to become long dumbbells. Right? And the long dumbbells have a high viscosity, relax their stress very slowly, and the short dumbbells have a low viscosity, relax their stress very quickly. What happens in this system, defined this way, is that above a particular shear rate, all of these so-called long chains completely fall apart. They can't support the stress anymore. They fall apart into these short chains. And hence, the stress falls off a cliff after a critical shear rate, and you get a system that shear bands. Now, this is an exciting hypothesis, but there are some potential concerns about the model. So first of all, the parameter space where shear banding is observed requires a large contrast in the viscosity of the, quote, long chains compared to the short chains, and the contrast is difficult to justify on physical grounds. Second, there is a non-physical truncation at just two species that leaves a wide gap in terms of, there's nothing to fill this gap in between of viscosities. And maybe that's why it sort of dropped, the shear stress drops off a cliff without anything else to fill in the space. And then finally, there's concern that while this model purports to describe well-entangled systems, since shear banding systems in worm-like micelles are well entangled, no physics of entangled systems are reflected in the stress relaxation dynamics of this model. All the species, whether they're the short dumbbells or the long dumbbells, are just represented as dumbbells. Okay, so our goal for this model is to describe something that has a single framework for the linear and nonlinear rheology predictions and overcomes some of these weaknesses of the VCM model. We're going to begin by way of review with population balances on the molecular weight distribution. So you have a molecular weight distribution that describes the number density of chains of any particular length. And we have in the figure here we've described that as a series of bins. And the idea is that with every reaction that takes place, material is moved out of one bin and into another bin. The lengths of these chains are changing, and you have this whole library of reaction processes, reversible scission and attack, bond interchange, by which that can occur. We're going to focus on just one of those. We're going to focus on reversible scission for the purposes of this talk. Now, the innovation of our model is that we're going to do the exact same thing that was previously done for the molecular weight distribution, and we're also going to do it for the stress. So in each one of those bins, you not only have a number of chains that occupy those bins, but you have an average stress that you could describe within each one of those bins. So the bins corresponding to short chains are not going to be holding very much stress. The bins corresponding to long chains are going to be holding more of the stress. And in addition, there's going to be processes of deformation happening in the system, stress relaxation, and then these reactions shuffling material throughout. So the easy ones to do are deformation and stress relaxation. For deformation, we're going to use the upper convective Maxwell derivative. That's what's used in the roly-poly model. And for relaxation, we're going to use the nonlinear relaxation processes of the roly-poly model. And those are chain retraction and convective constraint release. And this representation of the nonlinear rheology of a well-entangled polymer for the roly-poly model has been extensively validated in applications for linear, well-entangled, monodisperse, unbreaking polymer systems. And we think it reasonably applies here as well. To move on to the reaction terms and how reactions shuffle stress through the molecular weight distribution, we first have to ask questions about what is preserved in the course of a reaction. So, first of all, we saw in the number density equations that there is a preservation of the overall chain length. The chain length 1 plus chain length 2 is equal to chain length 3. And if you get into it, you'll notice also that there is a preservation of chain configurations, which also implies a preservation of stress every time one of these events takes place. That if two chains link up or break apart, that act of linking or breaking doesn't change the stress that's in the system. So with that in mind, we can go through the whole catalog of possible reactions that can occur and possible events that can move material in or out of any one of these bins, and that gives you these different descriptions of the shuffling process for the stress. And you can solve that. You can discretize numerically and solve this model. Okay, the final component to be able to look at the effects of flow-induced scission is to be able to describe how the configuration of a chain changes its reaction kinetics in the population balances. So first things first, we're going to say that the attachment process involves the free ends of these chains. Well, the free ends are always supposed to be at isotropic relaxed configurations. That's not going to be affected by flow. What is going to be affected by flow is the breaking process. How much stretching energy have we put into these chains? And that's going to make them more likely to break. Okay, so in the left-hand corner here, we have our test chain that I've drawn, and we zoom in on one portion of that test chain, and we show the different kinds of shapes that the contour can be adopting at different points along this reaction coordinate from a contiguous chain to a broken chain. At the beginning, it's roughly cylindrical. At this peak here, you get this neck shape, and then after that, it splits apart into two independent chains. And as you apply a flow, and as you cause this system to stretch, what you're going to do is you're going to raise the floor of this free energy on this side over here due to the effect of stretching. And so that's going to shift your reaction constant for breaking by that amount. So more stretching means faster breaking systems, means shorter chains, and so on. Now, rather than present all of the governing equations on a slide here, that slide would be too busy. It wouldn't really say very much upon a cursory inspection. I want to be able to take the time to discuss the dimensionless parameters that govern this system. We put all the physics in. The first thing is the entanglement number. Longer chains mean more well-entangled chains, which means that you have a wider separation between the relaxation times for chain orientation and chain stretching. And that's going to give you more shear thinning behavior, and potentially more shear banding behavior, when the system gets above a Weissenberg number of 1. The next parameter is the parameter zeta. Zeta is the ratio of the typical times for breaking and for reptation. as you get to faster breaking times, you get to systems that relax their stress faster. Basically, every time a chain breaks, it gives it new opportunities to relax its stress faster, explore faster relaxing portions of the relaxation spectra of the whole molecular weight distribution, and so on. Next, there's this parameter beta, which is an inherited parameter from the roly-poly model that describes the effectiveness of convective constraint release. So values of beta equal to 1 or larger are going to give you systems that do not shear band in steady flow. So we're going to fix the value of beta to unity for the results that are presented here, so that flow-induced scission is the only viable explanation for shear banding if it occurs in the predictions. Final parameter is alpha E, and alpha E basically tells you over how many possible breaking sites you have to divide the energy of stretching that you've put in to the chain. So the more you have to divide that up, the less susceptible the chain is to flow-induced scission. So larger values of alpha E mean systems that are not susceptible to flow-induced scission. We'll start here with predictions for linear rheology. Once again, we parametrically plot the loss modulus and the storage modulus over a range of frequencies, and we see that moving from a slow breaking system into a fast breaking system, we recover this semicircular shape, indicative of a single relaxation time. So that's good. Next thing is that if we look at the terminal relaxation time and how that changes with zeta, we again see that the terminal relaxation time decreases with decreasing zeta. And we get a power law of zeta to the 1/3 in the very fast breaking limit here. That's different from the power law that is supposed to show up if you include the correct physics of a full chain depiction of the reptation process. That zeta to the 1/2 is the correct result in that sense. Well, we know how to fix our model to recover that result, but that's outside of the scope of this particular talk. Here, we're interested in looking at the nonlinear rheology predictions in steady simple shear flow. Does it shear band? So the predictions that we've presented here are for a system with 100 entanglements per chain. That's a high number of entanglements. Alpha E equals 1. This is a system that is very susceptible to the effects of flow-induced scission. And beta equal 1. This is a system that would not shear band if not for the effects of flow-induced scission. So we're specifically evaluating the potency of flow-induced scission for creating a shear banding instability. And what we see from these predictions is that the shear stress is a strictly increasing function of the shear rate across all these values of zeta, from systems that are somewhat fast breaking to very fast breaking. Why is it? Why aren't we seeing a shear banding instability show up here? Okay, the short answer to that is basically that if you want chains to get shorter, they must become more stressed so that they start to break faster, right? So with increasing shear rate, you can have increasing stress that causes chains to get shorter. But that means that with increasing shear rate, you've also got increasing stress. And so you don't have a system that can shear band. The stress has to be increasing in order to support a decrease in the length of the chains in this population. And that's why flow-induced scission is not a viable explanation for shear banding in living polymers. This doesn't tell us what is a viable explanation, unfortunately, but being able to exclude one answer is useful, and to be able to have a model that can be extended to include more realistic physics is also useful in the pursuit of that answer. Okay, briefly I want to discuss some recent progress that we've made in light of some potential criticisms that could be raised against the model as presented here. First, one could say that starting from the roly-poly model is a little bit dangerous because it's not a full chain constitutive model. It's a single mode approximation that's fit to monodisperse unbreaking polymers as opposed to polydisperse reversibly breaking polymers. And in response to that, we have a publication that's recently been accepted to the Journal of Rheology, where we show how to construct these exact same kinds of population balance equations in the constitutive law for full chain constitutive equations. A second criticism is that with all of these integrals in the constitutive equation, is this something that really could work for CFD applications? And the answer is yes. We've found a spectral discretization method that produces great results with as few as just 6 modes. And that should be coming out soon as well. Okay, And with that, I would like to thank my advisors, especially during my PhD when this work was done. Gary Leal and Glenn Fredrickson made this work possible. And I have ongoing support for my continuing work on worm-like micelles from my advisor, Mike Cates. And that will conclude my talk. If there are any questions or follow-up, please do not hesitate to contact me. I would be very happy to engage and answer and talk about this work in depth more. So thank you so much for your time. Thank you for listening to my talk.